Okay, hi everyone. Good morning, good afternoon, good evening, wherever you are in the world right now. I hope things are well. Today we are very excited to have Susan Athey giving today's virtual advances with field experiment seminar. Susan is the economics of technology professor at the Graduate School of Business at Stanford. She's also the senior fellow of the Stanford Institute for Economic Policy Research. She's also the founding director of the Gulub Capital Social Impact Lab and the associate director of the Stanford Institute for Human-Centered Artificial Intelligence. Many of you might already know of Susan's work in IO, microeconomic theory, and also applied econometrics. And what I really like about Susan's work is sort of the application of experimentation and machine learning in cooperation with business and trying to understand how that impacts on markets. So today's talk by Susan will be designing adapted field experiments. One of her co-authors, Vitor Haddad, is also a panelist. So if you have any clarification questions, any questions that come to your head, feel free to write them in the Q&A and Vitor will respond to them. If there's any sort of recurring questions that come up, I'll ask Susan as we go through the talk. So thank you, Susan, for joining us, and over to you.
Great. Thanks so much for having me here. I'm really excited to be here. And I'm going to talk today about two papers, both of which are joint with Vitor. The first one is also joint with Jan Spies, who's my colleague here at Stanford. And then the second paper is joint with a team of people from Stanford, including David Hirschberg, Rohan Zahn, Stefan Wager, and Vitor. And in a little bit more of the computer science tradition and the ordering of the co-authors there, Vitor is the lead author, which indicates that he did the most of the work and led the second paper. And the advisor is last. I need to start putting more asterisks on all my papers because the ordering of authors in my life now varies from paper to paper. So I want to talk about these two papers, and just to give a little bit of an introduction, as many of you know, I've been doing a lot of work on machine learning and also designing A/B tests in the environment of technology firms. In my lab today, we're working with a lot of social impact organizations, ed tech startups, and training organizations to try to help them optimize their delivery for social impact. And one of the things that I encountered relatively early on in my work with tech firms was the fact that, first of all, A/B testing was prevalent. Doing large-scale field experiments is, of course, an integral part of the operation of every firm. At this point, all of you all know that, all the tens of thousands of experiments that are run every year. On the other hand, even maybe 11, 12 years ago, there was a lot of interest in the scientific community, particularly in computer science, on adaptive experiments and in particularly on multi-armed bandits. But yet there was relatively low take-up even in the most sophisticated tech firms, which has started to change over the last 5 years. But it was actually relatively slow. You might have thought like something like MSN would be doing multi-armed bandits to try to figure out, which is the best news article to put on the homepage. Even 10 years ago, because people understood the theory and this was an obvious application. But it's actually been slower than you think to get these things into practice. Maybe I should have been cautioned by that, because maybe 5 years ago, I thought, well, okay, I'm going to go do these in academics and there's going to be so many great applications and I'm going to build a platform and I'm going to start running them. And I would have thought by now I would have, a whole suite of, 10 applications all complete and, ready to go. And it's actually been a bit of a much slower slog than I expected in this area. So I'm going to sort of tell you about, I think, some of the promise, but I also want to highlight some of the challenges as well and some of the reasons why it's been hard. And that's going to be really the focus, especially of the second part of the talk. Every time we've gone to write a pre-analysis plan and try to do simulations, we've ended up not getting the results we expect, not getting the coverage of confidence intervals that we were hoping to get, and so on. And so actually, there was more theory left to do than I thought there would be. And so we've been working both on the applications and the theory. So just to then give an overview of what I want to talk about today. First of all, randomized controlled trials. So hopefully everybody on this call are believers. So no extra explanation needed for that. They obviously allow for transparent inference of causal effects, but they actually is a relatively high cost. So we might end up randomizing many people to a bad intervention using an RCT. And that can be particularly problematic if I'm in an environment where I'm, thinking about vulnerable populations, I'm thinking about school kids, we think about health interventions. There's sort of ethical issues involved with doing that. And the data collection may also not be aligned with your experimental objectives. So depending on what you want to do with that experiment, a purely randomized RCT may not actually be the thing that optimizes your welfare. And I want to highlight, it's kind of disappointing to me in a way that the computer scientists sort of ran off with bandits and adaptive experiments more so and faster than the economists, because actually, in many cases, we argue the computer science community isn't really taking the right economic approach. They're not thinking about incentives, blah, blah, blah. But in this particular case, a lot of the computer science framing is actually very much of an economic one where there are trade-offs and there's an objective function that you're optimizing. However, what the computer science community has sort of zeroed in on one particular objective, and we'll talk about how different objectives might be more appropriate for economic circumstances. So in this presentation, I'm going to talk about adaptive experiments as alternatives to RCTs. I'm going to illustrate how adaptive experiments can be used for pilot experiments, in which case actually you don't have to worry too much about theory and they're relatively easy to run since all of the statistical theory will come in the second part when you run your real experiment. And I think this is sort of a no-brainer to do, and I do expect that using adaptivity for pilots or early stages of experiments, my prediction would be that that's going to become much more prevalent going forward. There's sort of not a lot of cost to it and a lot of upside benefit. But then I'm going to talk about statistical approach challenges associated with using adaptive experiments as your sort of main experiment and the one where you want to draw conclusions. And there's a lot of challenges around inference there. And so I'll talk about the advances that we've made to try to make that easier. But those challenges, are not, it doesn't come for free. The adaptivity is not free. And so you need to think about the trade-offs at that point. So just to kind of build intuition, if we think about a purely randomized experiment, suppose we have 4 treatments, we do a uniform assignment. So we're going to have the assignment probabilities in this first chart. They're equal, roughly equal units per treatment in the actual experiment. And then if we just order these in terms of how good they are, we're going to get 4 estimates with 4 standard errors. And the problem with that is that first of all, many individuals are going to be assigned to suboptimal treatments. And in the bandit literature, that's called regret. And regret is basically the difference between the welfare of the individuals in your experiment and the best welfare that they could have been delivered. So in this case, the maximum welfare, the zero regret case, would have been to put everybody in arm 1, treatment 1. But we put people in others, and that creates a welfare cost for those users. And just to remind ourselves, like, why would people? We usually think about experiments as sort of scientific discovery, but if you're running a tech company or something, you have people coming in all the time, and you're experimenting all the time, and so the weight tilts the other way, and you want to just think about, I'm always experimenting, and so I want to think about the utility of the users that are as they come in the door. Rather than some hypothetical future. And so the other problem with this is, suppose that T4 was the control. So we're trying to improve things. So we have 3 potential improvements, and the control is the worst. We might want to test a hypothesis about the difference between, say, the best arm and the worst arm. And in this case, we don't know too well how good the best arm is, and we also we have a lot of precision about arms that aren't really relevant for that comparison. So instead, if we run an adaptive experiment, we start at the beginning just the same as normal, and we assign uniformly at random, and we now just in the first batch, now we have a small number of units per treatment, so we have wide confidence intervals around each of the arms. But it looks like one of them is ahead. And so what you do then is depending on which algorithm you're using, but I'm going to talk about Thompson sampling, you compute which one you think is most likely to be ahead, and you actually compute the probabilities that each arm is the winner. And then in the next round, you assign the probabilities associated with which one is most likely to be the winner. So, So then you're going to increase the assignment probability for the things that are doing well and decrease the assignment probabilities for the things that are doing badly. So then in the next batch, we've now loaded up more observations on the good treatments and less on the bad. And so now you can see that the confidence intervals are much narrower for the good treatment and they're worse for the bad treatment. But because you're uncertain about the bad treatment, you still do assign to the bad treatment. You don't have that much information, and so there's still some chance it could be good. And so you will still keep loading up observations onto the bad treatment until you've narrowed the uncertainty enough so that it's unlikely to be the winner. So it's not just the means that are determining this, but it's also your uncertainty, which is why you don't shut down the fourth arm altogether. And so we keep doing this, and then by the end, you have very precise estimates of the quality of the best arm, and less precise estimates of some of the medium arms. And depending on your objective, that may be exactly what you need to know. Now, you can already see, though, there's going to be trade-offs because you might have a primary hypothesis, something like, I want to see if any of these arms is better than the control, or I just want to pick something that's good. And I'm not that concerned about which one, but you might have secondary hypotheses where you want to see, well, maybe there's something special about arms 2 and 3, and I want to see, is that special thing associated with better performance? So you might want to do other kinds of contrast for secondary hypotheses or to guide future experiments. And then you've potentially made yourself better positioned to answer your primary hypotheses, but potentially less well positioned to answer secondary hypotheses. And so one of the challenges that you would like to set out in, they say, a pre-analysis plan is you might want to balance the ability to test multiple hypotheses when you do your pre-analysis plan. And so that's a kind of thing that's trickier and harder, and we've been developing theory that can help with that. But for now, let's just keep going here. As the experiment's progressing, finally, by the end, we've got lots of observations assigned to the optimal treatments. You have lower regret and tight confidence intervals around the optimal treatment value estimates. And for some objectives, that might be a good goal. So now let me talk a little bit about the heuristics for bandits. And again, you need to dig more into this, although I'll caution you that it's actually quite tricky to read this literature. Like if you try to read the computer science papers, like, I'm sorry, because they're all, very short papers and they don't give a lot of sort of intuitive explanation. So, please email me if you want to see more reading that's kind of user friendly. But I want to explain one of the most popular algorithms and the one that is particularly appealing for, I think, economists to build on. So Thompson sampling basically is an algorithm, and it's been proved, and I won't show you the proof today, it's been proved that this algorithm has nice properties in the sense that if you use this algorithm, you'll get good regret properties. And it's not going to be obvious why this works. And I'm not going to tell you today why it works. I just want to tell you, though, you shouldn't think it should be obvious to you that it has these properties. It requires extensive proof. But just to tell you how the algorithm works, basically what you do is you start with a prior distribution on arm values. Then you collect a first batch of data by assigning treatments uniformly at random. The next thing you do is you observe the outcomes and update the posterior distribution. And finally, in the next batch, you assign treatments according to their posterior probability of being optimal. So you can see in this left graph, the prior probabilities, they're going to be the same for each arm. And you have to specify a mean and a variance at that point, or you can, you can use various priors depending on what your circumstances. But then after you've seen the data, then you update. And so in this particular example, arm 2 has a higher mean. And this might be after a few batches, it's got a high mean and a tight variance. Then some of the lower arms have lower means, and also potentially, for example, if you had less data collected, you might have more spread. And so you're going to look at those full distributions and realize that something can have a probability of being the best, even if it has a low mean, if it has high variance. And so that's what you're going to be balancing. You're going to keep collecting data until you're sure that an arm is best. This is, and of course you can, typically in an economic context, you might want to put lower bounds on the assignment probabilities, and I'll come back to talk about why that's useful for inference and stuff later as well. So this heuristic, as I said, it has good properties, and in terms of minimizing regret in the experiment. And so it's been proposed as a way to minimize regret, not as having anything to do with hypothesis testing. So that's what it's sort of known to be good for. Now, yes.
Maybe that's a question about
yeah.
That contrast that you made between computer science and economists in using this. And so David Riley at Pandora has a question about, he sees a lot of his computer science colleagues very fond of using this technique, but they're also looking at sort of more short-term immediate behaviors, like did the user click this link or did they, click that tab? But some of the decisions that we all are looking at are more longer term. And so do you have a sense of like how you trade off the sort of the short-term optimality of this versus like the long-term outcomes, looking at, unemployment or sort of longer-term welfare indicators that we might care about?
Excellent. Thank you so much for asking that question, David. So, and David knows that's a near and dear question to my heart. So thank you for letting me get on my soapbox for a minute about that topic. In tech firms, one of the biggest mistakes that I see systematically made across all tech firms is that everybody gets very short-term focused. And actually, if I teach an MBA class or an executive class, I'll spend an entire class talking about this. So, if I'm teaching 2 sections, the first one will be like, oh my gosh, machine learning and adaptive experimentation, they're so awesome, they're so great, you should go do them. They look at how amazing all the tech firms have done with them. And then the second section is like, oh my gosh, here are like the 10 things that go wrong. And they go very wrong. And the number one thing that goes wrong is short-termism. And there's a very good reason for that, because if you are doing lots of A/B testing, then you have the ability to learn quickly, but only if you can measure your outcome very quickly. It's not very helpful to have rapid experimentation if you have to wait 6 months for the results of each experiment, or wait a year. And of course, many fundamental economic questions for businesses, especially like marketplace businesses, are longer term. Like a market needs to come to equilibrium. If you're changing, what happens on Uber with the drivers or something, the market needs to re-equilibrate. If you're looking at competition among, sellers on eBay, it takes a while to equilibrate. Ideally, for many things that a firm cares about, you would like to run a long experiment, but then there's a real trade-off between being able to rapidly learn and innovate and actually optimize for what you care about. So in a series of papers with Hito and Raj Chetty, we've been working on surrogate outcomes. Raj Chetty's interested in them because he wants to, think about running experiments on schools or other things, and then try to have a proxy for the long-term outcome of the students. And so we have some examples there. But in tech firms, sometimes it's like people are optimizing for clicks or views, and you'd like to understand better what's a metric that represents long-term. And so, for example, looking at long dwell time or user engagement can be better than clicks because it better represents something that might make users happier in the long term. So you can put a Band-Aid on the short-term problem by trying to optimize for surrogate metrics that are carefully designed to be non-manipulable and optimized for the long term, and to represent the long term. But it's just a Band-Aid, because it's never really as good as actually optimizing for long-term objectives. And so I believe that sort of the second best strategy for a tech firm is to optimize for the wrong objective. Because you can go so much faster. But then you put in other guardrails and organizational limits to keep you from that. So going back to so why did I go on this long tirade here for this audience? I think that, there's an analog of that in the scientific literature, in the sense that, I find myself doing that now. I want to show adaptive experiments. So I go out and do a quick experiment where I can optimize for something. I'm going to run an experiment on Facebook, and I'm going to measure clicks or views on a website as my outcome, instead of whether I really improve somebody's quality of life or their health. And, maybe that pushes science in a bad direction. And so just like I put up the big caution flags in the tech companies, I think we also have to have the big caution flags up for us as scientists. But I think there's a balance. So we should try to use these adaptive techniques with short-term outcomes and these kind of quick turnaround field experiments for parts of our problem, but we shouldn't stop doing the longer term, more expensive things that also give us maybe deeper insights about the things we really care about. So I think there should be a balance. So I hope that answered your question. But I'm very passionate about this topic, if you can't tell, both on the positive and the negative, if that wasn't completely clear. Okay, so now let's talk, but that actually segues very nicely into my next point, which is that what is the objective of your experiment? So the computer scientists kind of have the idea that we just want to minimize the regret of the people as they come through. As scientists, we might actually want more of a balance between those things. We might care about the subjects in our experiment. We don't want to hurt them too much. But we also want to learn in the future. In the literature, there hasn't been that much in that middle ground, but we have seen stuff around things like what's the best arm identification. So it might sound like a good objective is I really want to make sure I figure out the best arm at the end. That's my goal. But actually, I would say that goal is not as easy to justify as it seems once you really think about it, because that might lead you to put like a lot of effort and units to distinguish between two treatments, which are really very close to each other, and there's very little welfare benefit of distinguishing among them at the expense of making sure that these two are the best relative to others, making sure that you haven't missed out on some other treatment that might have just spuriously looked bad, but might turn out to be good. So I think an objective that might better reflect economic considerations is something where you're maximizing the welfare or the value of the arm at the end of the experiment, rather than just arbitrarily wanting to know that one is best. And from a statistical perspective, that can matter, because actually there's a lot of edge cases where if two arms are actually identical, it's really hard to tell them apart. And bandits are also like pretty unstable at telling apart things that are very, very close. So if you want to really think about just welfare, maybe you want to put less emphasis on just getting the right arm. And Max Casey has a recent paper, it's coming out in Econometrica, where he's looking at exploration sampling. And that's basically an algorithm that he's proposed that looks at trying to maximize the welfare at the end of the experiment. And I might argue that, especially in pilot studies, that might be the right objective for you. You're trying to narrow down your alternatives and find something that's good, but it may not matter to you so much, to understand the difference between the very best arms. You just want to look at the value of what's coming out. But in general, I want to say that there's not just one right objective. You need to think about your problem and decide what it is you care about, and then try to optimize and try to develop an approach for that objective. And that's something I think economists are good at, is stepping back and thinking about what's the point of what we're doing to start with, and let's make sure we're doing the right thing for that. Okay, so then what I'm going to do is show two cases, again, kind of positive and negative. I'm going to show a pilot study that we ran and how it was helpful there. And then I'm going to show look at inference and theory around inference. So the first paper is a collaboration we did with Ideas 42, which many of you know in this community. And they were working with the New York City Department of Finance to look at the problem of people who getting their cars booted. So if you accumulate more than $350 in fines, it's eligible for booting. And the problem is trying to get people to engage with this and resolve their parking fines. Now you might think that, oh gosh, where's the social impact in getting people to pay their parking tickets? But I'll remind you that as those of you who thought a lot about behavioral finance know that, one way that people can go from sort of bad to worse in terms of their financial situations is to get into a situation where they're paying fees and fines, whether to their bank or to, in this case, the government. And those fees and fines are particularly a big hardship on the poor. So the partners at Ideas 42 designed 9 prototypes targeting different kinds of behavioral bottlenecks, lack of attention, unwilling to face responsibility, et cetera, to improve the email. And it was basically a 3x3 design on the email and the subject line. And so what they then asked for our help with was trying to narrow down which of these prototypes would actually go to a full experiment. And as I mentioned earlier, the advantage of narrowing things down is then at the end of the full experiment, you'll actually know something with confidence about the good arms. So if we just run this as a 10-way uniform RCT, pre-analysis plan would indicate that we're just going to have sort of noisy estimates of all the arms. And so we won't really have a precise estimate of anything at the end. So instead, we're going to do this pilot and then take that to the main RCT with just 2 treatment arms. So to do the pilot, we ran it on Amazon Mechanical Turk. Yes, like big caution tape, like Mechanical Turk is terrible for 15,000 reasons. Actually, somewhat surprisingly, like it actually worked pretty well for us, and our estimates were not that far off of what actually happened, but that may have just been luck. So we worked on Mechanical Turk. We gave them a simulated email inbox with a subject step where participants rated the priority level of different subject headings, and an email step where they were asked to imagine they received this and they had the option to either click or delete. And the adaptive experiment sought to maximize the desired behavior of engaging with these things. So in this experimental design, here's an example. We would show them an inbox. We put this orange box around there. It wasn't there. And they were asked to rank the subjects in terms of their priority, and the subject order was randomized. And so we just mixed in this email headline with other things from a typical email box. So when we looked at these subject lines, we had the at-risk subject, your vehicle's at risk for towing, an action subject, pay now to avoid towing, and a personalized subject, which says like your plate is at risk for towing. Now it turned out that turned out to be too hard to implement in practice. So we didn't actually do that in the real experiment, but we weren't sure at that time. And just to think about, like, one advantage of the pilot is to say, if this is like a zillion times better than everything else, then maybe you do the engineering and go through all the legal to do this. But if it's about the same as everything else, then maybe we just stick with something simpler to implement. And so this is one of the email prototypes. There were clicking on these links, which we've highlighted here in orange, like click to pay your parking ticket or click to dispute. And they could also click on the trash. And this was the control email that had been previously sent by the Department of Finance. And so there was a number of things that Ideas 42 was improving about the email to try to improve action. So then to collect this data, we used a modified Thompson sampling algorithm. We modified it first to make sure we had sufficient observations allocated to the control, because we did anticipate wanting to be able to say that the treatment is better than the control, and otherwise the Thompson sampling wouldn't put enough in the control, and that we thought the control was likely to be bad, which it was. In fact, in practice, we used a contextual bandit, and we had originally thought we might run the experiment longer and actually get a personalized algorithm. But then it ended up, because of timing and other issues, we didn't collect data long enough to really be able to learn anything about personalized. So I'm going to show you today as if we hadn't done that personalization. And you can just think about that as sort of background noise or additional source of randomization, that in practice we responded to user attributes, but because there was random assignment, those user attributes would just be random from the perspective of the experiment. And so we can see after the non-adaptive phase, you can see the posterior distributions illustrated here for each of the arms. At the end of the experiment, we had put a lot into the control, so we have a fairly precise estimate of black in the control. And then we have posteriors that basically put 3 of these treatments seem to be kind of in the lead in terms of what their algorithm believed to be true. We then took 2 prototypes. Now it turned out, again, this is not as pretty a paper as the idea was this paper was going to show the whole pipeline end to end, but as you know, life happens, and we weren't actually able to implement the actual things that were selected by the prototype. So they motivated what we did, but that was subject to more organizational constraints on the part of the partner. And the main RCT used 2 arms with 22,000 actual New York City drivers. And we found that both of the prototypes were better than the control. The baseline probability was relatively similar to what we got out of the Mechanical Turk. So then we asked the question, so that's basically all I'm going to say now about this field experiment. Again, in an ideal world, that we would have planned this all end to end and it would have gone perfectly according to plan, but in the end, there's a few of these glitches. Maybe one other glitch I want to emphasize is that we actually used Thompson sampling, partly because we wanted to use contextual bandits. We had all that coded up and tested, so we ran Thompson sampling, where really for a pilot study, we should have been using exploration sampling and trying to optimize for welfare at the end of the experiment. So one question we had at the end also was, well, we actually, this isn't a pretty design because we didn't actually follow our own advice and try to optimize for the right objective. We just did what was convenient quickly. And did we actually hurt ourselves by using the more established and commonly used Thompson sampling instead of something like exploration sampling? So we had those questions. And so the way to answer those is we actually did a set of simulations. And one thing I want to emphasize is that with bandits, you really do have to simulate in order to understand whether your algorithms are working. Because typically, like if you're doing offline evaluation, what we typically do in economics is we have an observational data set, and then we can estimate like, well, we can do counterfactuals. What if everybody been treated? What if everybody been controlled with that observational data set? A bandit algorithm is active exploration. And so it's going to tell you, which units should be assigned to which treatment at a point in time. And so to simulate data as if it had come from one bandit or another, you really have to simulate sort of going through that process of doing assignment iteratively. So we're doing simulations here to see what would have happened. There are some ways, if you have a very big data set and you're not doing things contextually, where you can try to simulate a bandit using actual data, but generally people do simulations here. So we run a simulation with 10 arms, 1,600 observations. The arm means are drawn from a beta distribution where the posterior is where that's basically related to our posterior after the mechanical Turk pilot. And we check 3 data collection methods: pure RCT, Thompson sampling multi-arm bandit, and exploration sampling. And then we want to see which of these potential pilot experiments would have done the best at helping us pick good arms for the subsequent experiment. So this is kind of what the data looks like, and we have a little Shiny app that does this, although we haven't posted it yet because we're still prettying it up. But if people are interested, I can show you the Shiny app that does this. You can play with this yourself. And so what we do is we look in every run, every time we draw the arms, one arm is going to be best and the other is worst. So just to simplify the presentation of the results, we reorder those 1 to 10 in order of the performance. And here I'm just showing you what, like, the best arm on average tends to get more data over time. The worst arms get less data over time. And then the arms in the middle are kind of in between. And then we see that exploration sampling tends to be more moderate. So exploration sampling is more concerned about learning and welfare. It's less concerned about what's happening in the experiment and more concerned about making sure we find the maximum welfare at the end. And so exploration sampling is more moderate. It doesn't put all the weight in the top arm. It gives more weight to intermediate arms. And so it looks like there we see that happening. We look at average regret. Random has the most regret because I don't stop giving to bad arms. Thompson sampling has the least regret. And remember, regret's the difference between the best possible and what actually happens in the experiment. And here we have x-axis is time. So as we go through the experiment, Thompson is giving most things to the best, and so it's got the least regret. And exploration sampling is in the middle. It sort of starts to slow down after a while because it wants to keep learning about the bad arms. Now, it turns out, though, in practice, with this particular design, Thompson sampling and exploration sampling actually did just about as well with all of our metrics. So here, optimizing for the right objective wasn't very different than optimizing for Thompson sampling. But there are settings where it would make a big difference. It's just in this setting, it didn't happen to make a big difference. And so we see that how often we correctly get the top arm is higher for exploration and Thompson than it is for random, and the same for top 2. So this is basically saying you're more likely to have a good outcome in your final experiment if you used adaptivity in the pilot than if you did it fully random. We can also look at the difference in value between the best outcome and what we get. And this is the real welfare. And again, we see in terms of welfare, exploration and Thompson sampling are much better than random in terms of making sure that the expected value of the best arm is the best. The arm you pick at the end is the best. Okay, so that was all about running pilots, and I think that's really like the positive story. Like, there's not much downside and there's a lot of upside, and you can think most of the time in designing experiments is human time, where you're arguing, well, should I do this, should I do that, should I change this wording, should I change that wording? It's all this whiteboarding and meetings and meetings and meetings, and instead here you can imagine, let's just cut the meeting short and run more stuff and let the data tell me and kind of narrow things down. So the stuff that you don't really have scientific priors about, just let the data tell you and focus your arguing on the science. And maybe you can run more experiments and get more research done. But then we want to consider, well, what if you actually want to run an adaptive experiment as your main experiment and you want to test hypotheses afterwards? Or even for the pilot, that like you did run a bunch of stuff and collect a lot of data, so maybe you also want to report some hypothesis tests out of the pilot. So we want to know what are the frequentist properties of the statistics we get.
Susan, just a quick question by Ben Marks. Actually, maybe it's a good segue for this question, but like, he thinks it's like a really nice way of estimates to get for the best treatment. But in some cases where we want to know, for example, or care about multiple things like an income effect or a price effect, and then add some structure to measure welfare, like can those kind of like structural models then be incorporated into this adaptive design?
Yeah, so I think that's a great area for further research. So again, economists are a little behind the ball there. The group that's thinking about that more is operations research. So the operations groups and business schools and so on have also caught on to bandits, and they're actually a little faster to get into the machine learning than economists have been. So there, people are often interested in pricing decisions, and people have looked at things like pricing. We actually, with another set of co-authors, Vitor and I are working on an experiment in Cameroon where we're looking at subsidies for long-acting contraceptives. And so there we are doing a bandit around, around pricing. But I would say that literature is much more nascent, and there's more bespoke work to be done to do that for a particular setting. So I think that's a great opportunity. What I found is actually most of the literature, where one place economics is actually ahead still is like structural modeling. And so actually bringing together machine learning and structural modeling is someplace where we still kind of have a bigger advantage in terms of methodology. Another place is actually, and this is going to come in this paper, where econometricians have thought a lot about the statistics of inference. And so one thing that bandits are basically doing is creating selection problems. And I'm going to show you that now. And it turns out that semi-parametric theory about solving selection problems, which are things that we've thought about for years, actually are quite helpful for doing inference with bandits. And so that's a good segue into the next thing.
Right.
So I don't have a ton of time. So I'm basically, what I'm going to try to hope in this part, I'm going to leave behind more slides that I'm going to go through, but I really want you to get the intuition for why inference is hard. And then I just want to advertise that we have a solution. And if I accomplish those two goals, then I will have hopefully succeeded. And I'd love to talk more about the details of the technical stuff. So here, let's think about now the point where we want to actually test hypotheses after an experiment. And so let's try to just build some intuition about what goes wrong. Now, you might think that I'm running an experiment and I'm randomizing. So, it's adaptive, but at every step I'm randomizing. So why can't I do inference? Why would inference be hard if I'm the experimenter and I know the assignment probabilities at every point in time? Why are things hard? So let's just think of a simple example. Suppose we have two batches. So we have a first batch where we run a purely random experiment and we collect the data. Then we look and see which one looks better in the first batch, which has the highest sample mean. And in the second batch, I assign the arm with the highest estimated mean 90% of the data and only 10% to the bad arm. Okay, let's see what happens. And so this is very simple, and you can solve this analytically. I encourage you to try this at home as well. You can run a simple simulation for this. So if I run the simulation and I estimate the sample means at the end, my estimator is just what is the sample mean, pooling all the data at the end of the experiment. This is what it looks like in a simulation. And so you can see that this is centered below 0, and our actual data is not normal. Okay. So what is going on here? It's biased and not normal, even though everything I did was purely randomized. And it's not like hyper adaptive, right? I just did something very simple. The reason is that when we get a low estimate of the average after the first batch by chance, and if two arms are equally good, one of them is going to be worse by chance. Then in the second batch, I don't collect very much more data. And so when I pull all that together, that's it. You can relate that to what happened if I averaged in the first batch and I averaged in the second batch. Because there's not many observations in the second batch for the bad arm. That's as if I upweighted that's as if I upweighted the initial batch, because the first batch overall is contributing more. There's more data points in the first batch. And so when I pull everything together, the first batch as a whole gets more weight. The second batch gets less weight because there's less observations there. But the fact that I had less data in the second batch is caused by the fact that the first batch looked bad. And so I'm essentially systematically overweighting data from batches where an arm looks bad. Because if it looks bad in one batch, I gather less data in the next batch. So that's equivalent to upweighting bad batches systematically. And that's why you get this downward bias. Now, you can also get upward biases in other situations, but that's like the easiest intuition. And so that also helps you think, well, what's the solution to that? I could instead just take the averages batch by batch, take the average in the first batch, the average in the second batch. Within each batch, assignment was purely random. And a priori, I don't know whether, you're going to get lots of observations or not very many observations in the second batch. So if I commit myself to weight each batch equally at random, equally, so then I will get unbiased estimates. So even though I might have 90 observations in the first batch and only 10 observations in the second batch, I nonetheless first take the means within the batches and then average them equally. And that will give me an unbiased estimate because it's basically undoing this overweighting of the bad batches. Okay, so that's a way to solve it. So just to see though how we get this non-normality, what happens is that you get, when you run the simulations, you can see when the ARM value was larger in the first batch, conditional on that, your sample mean is actually higher than average. When the first batch was the lower one, you get a lower than average estimate. And so when you pull together these two biased estimates, because of course in the beginning you don't know whether you're going to have spuriously good or spuriously bad estimates in the first batch, you get something that's non-normal, kind of has this hint of being multimodal and has weird looking tails. And also those things have different variances as well. So you get this weird shaped final distribution, and that makes it very hard to test confidence intervals. So, it took us quite a while to figure out why in our simulations we never got good coverage of confidence intervals, even when we did reweighting, and this is basically why. So what we do the reweightings I mentioned is a way to fix the problem. One thing that's a little weird is we're going to call this propensity weighting even when there's no covariates. And so I just want to highlight it's propensity weighting. It looks the same as propensity weighting. We're going to use the words, but there's no covariates. So what we're doing here is weighting batches. So the thing that's like a covariate when you estimate a propensity score is the batch identity, not some characteristic of individuals. But it turns out the statistics are actually the same. And so that are similar. They're going to be dissimilar because we have correlation in the data, and I'll come to that in a minute. So what way we can solve this is we can weight the observations. This ET of W is the assignment probability at time t for arm W. And so for every observation, we're going to use inverse propensity weighting, and that's essentially the same as weighting all the batches equally, which gets rid of the bias. Can we use it? Well, this is what happens when you use inverse propensity weighting. Here's my picture. So now it's going to turn out that this is unbiased, but you can see that we still don't have a normal shape in the actual data. And there's a couple of reasons for that. And that was the part that was less obvious to us. And this caused problems with the coverage of the confidence intervals because you can see the shape of the tails is also not normal. So it's not just that it's not normal, it's also high variance because you get these small assignment probabilities and it causes the variance to blow up. And that's basically a formalization of why testing hypotheses after adaptive experiments is hard. So the basic problem is that even though we have these average of unbiased terms, the assignment probabilities go to 0, things blow up. And so what we're going to do is we're going to try to use non-uniform weights for these observations in order to damp this down. So we know at the end of the experiment, we're going to have some arms, we don't know which ones, are going to be not have high assignment probability, so they're going to be high variance, and maybe we can take advantage of that in some way to dampen their importance and therefore reduce the variance. On the other hand, that's going to cause other problems. So it's how do you do that well, and how do we know whether that solves the problem? So we can start with an IPW estimator, which is just going to be, as I said, reweighting batches, and we're going to say that the typical estimator would be to equally weight all observations once they're propensity weighted. And so what we're first going to do is augment that with a AIPW estimator, which many of you know is a doubly robust estimator, where we basically estimate the means of each arm and kind of average that in. And it's going to be our running mean at this point in time. And that's essentially going to have the impact of upweighting earlier observations already in order to kind of keep things from blowing up. But it's still not good enough because you still have these propensities in the denominator. So our insight is that we're actually going to construct new weights, and those new weights are going to really be optimized to minimize variance. And so they're going to have the property that they're going to put more weight in the early part of the experiment and less weight later in the experiment. And so the idea is that we can then use martingale theory to figure out what properties those weights have to satisfy in order to get us a central limit theorem. And we can find weights that basically minimize variance while still respecting central limit theorems. And we can further optimize variance by actually making these adapt to the past. So we don't just have to pre-specify the weights at the beginning. We can actually kind of look at what's happening, look at the early data, and use that to adaptively downweight. So if an arm is starting to do badly, we can sort of we can anticipate that we might need to downweight later observations more and upweight earlier observations. And the key for the martingale theory is that the nature of the correlation in this problem is that you look at early data and use that for later treatment assignments. And so we can do whatever we want by looking, when we evaluate things, looking at past data, but we want to be very careful sort of not to look at the future when we weight today's data, because we're already using today's data to assign in the future. And so we don't want to kind of mix those things up. It induces correlation that's hard to deal with. So we end up, just to recap, there are two kinds of weights. The first type of weights are about getting lack of bias. That's these propensity weights. There's a second type of weight, which is weighting observations as a function of time to try to reduce variance. And so let me just skip ahead here. What we do is we end up proving a theorem that under some conditions, our weights will give us a central limit theorem and asymptotic normality. And then what we do in our paper is actually derive the properties that those weights have to satisfy, and we propose a particular category of weights that will always satisfy the conditions. So if you use these weights, you know you're going to get a central limit theorem, and you're going to be able to use them to control variance. So just to kind of recap, we started with this IPW estimator, we replaced it with an adaptively weighted estimator, and we want to figure out which weights we can use. Let me see if I can skip ahead to kind of go through what the way these weights work. So a first thing we can look at is uniform weights, which is basically just we weight everybody uniformly. That was the thing we were trying to beat. A second thing we can do is actually try to make the weights proportional to propensity score. So we're dividing by the propensity score, but we also going to multiply by the propensity score. That's going to undo the propensity weighting. And so that's going to be good for variance, but it's going to create other problems. And one of the problems is if we want the weights to add up to 1, then we end up sort of violating our conditions about not using weights that depend on the future. And that causes problems for the central limit theorem. Another thing we can do is use weights that are proportional to the square root of the propensity score. And that basically allocates a constant share of the variance to each observation. And it's a heuristic that's basically trying to say that each we're gonna try to think about reducing variance by having a heuristic that every observation should contribute equally to the overall variance. That's going to satisfy the central limit theorem conditions, but it's not the optimal thing from reducing variance. And so then we come up with a scheme that is better than that optimizes for variance reduction. So we then do some simulations. I don't have time to kind of go through all of those, but they sort of end up illustrating. Let me just come to the kind of conclusion. What we see is that these uniform weights don't satisfy central limit theorems. So those are in this middle panel, like on the left, we see non-normality in things. As expected, these weights that are proportional to propensity score have low variance, but they're also not normal, especially if the data is noisy. And what we do gets variance that's close to the best, and it's especially important in the high signal cases. And it's going to allow us to do inference and get good coverage afterwards. But even here, we would caution that you do have to have enough data to get to the point where you get good coverage, and these things are still relatively delicate. So I didn't give related literature. Here's a slide. I can post the slides later, and you can take a look at it. Just to sort of conclude, we believe that adaptive experimentation is an underrated statistical tool. It can help you quite a bit in terms of being able to explore more and be able to kind of get to your objectives for a lower budget, basically, and really learn most precisely about the things that matter most for future implementation and also for scientific hypothesis testing. Because again, there may be some hypotheses you want to prioritize more than others. But more sophisticated tools need to be deployed for inference, especially in frequentist settings. And the paper I just described is really an input, because once you know what the variance looks like afterwards, which we had to derive in this paper, then you can do your pre-analysis plan. And once you know when you have a way to calculate variances, you can optimize your pre-analysis plan for your objectives and make these trade-offs. And it might suggest that you need to keep more data in the control group, or put a bit more lower bounds on your assignment probabilities, or have a less aggressive algorithm, use exploration sampling, or even something more damped to that if you really care about testing hypotheses at the end. But as long as you know how to test hypotheses, you can, which we're trying to move towards, you can do that and do your planning around it. But you still need to exercise caution, and these things still are complicated. A question I didn't answer yet, which we can discuss further if you like, is why the hell are you doing hypothesis testing to start with? Maybe this should just be a decision tool, and we should abandon frequentist inference altogether. My short answer to that is I'm serving you all with my methods. And as long as you guys want to test hypotheses, I'll try to produce methods to do that. And then there's, of course, a longer answer that there are many times when the community's desire is, in fact, appropriate. So let me stop there and we can go to more Q&A.
Awesome. Thank you so much, Susan. That was fantastic. I think we all learned a bunch doing that talk. And we'll obviously post this talk on the YouTube channel so people can see the slides. And obviously that'll be fantastic. There's a few sort of running themes of some of the questions. There's sort of two on heterogeneity. So David McKenzie asked the question, how do you think about treatment heterogeneity in this setting, with the possibility that different treatments might be best for different people? You mentioned contextual experiments, but does this contextualization also adapt over time? Or do you need to pre-specify what dimension of heterogeneity that might matter to you? And then Seema Jayachandran asks, it seems like a useful application when the objective function includes a do no harm principle. So the welfare is not smooth in the effect size, but discontinuous for negative effects. And so is there work out there to sample in that setup? And I think they're both trying to get at, so there's a lot of heterogeneity in the effects that you might find.
Yeah, so I think actually I didn't talk as much about the medical literature. There's a couple of literatures on adaptive experiments, and the medical literature has really been focused on some of these objectives around, you know, when do I throw an arm away, and also, like, you know, and they're very worried about throwing arms away, because if they start seeing that a treatment is hurting patients, you need to throw it away. So that's an old literature. It has many strands. One of them is Bayesian. So I do agree, if you're more interested in that, especially in medical experiments, there's more literature there to look at. Coming back to David's question, so when I originally started, I thought, you know, oh, well, the regular bandit problem is already solved, so we're going to jump right into contextual bandits. And that's where actually economists and econometricians might have a lot of advantage, because then we would be thinking about propensity score weighting as a function of X's, and we would be trying to learn personalized treatment assignment policies, which is what I had been working on. And I just kind of diverted back to the regular bandits because we actually realized we didn't understand all we needed to know about regular bandits. So what I've learned about contextual bandits, I have a couple papers, some in computer science journals, that are actually trying to bring in ideas about econometric inference to contextual bandits and try to make them better. And so in the contextual bandits, it's everything we just said, but conditional on an X. The literature there basically starts, the leading papers in the computer science literature basically run regression models. So you, after every batch, instead of computing sample means, you run a regression where the outcome depends on both the treatment and also covariates, and then computes posteriors about each treatment arm conditional on X's. So you might use like a ridge regression model if you wanted to be, you know, Bayesian, and just you do everything conditional on covariates. And we also, Hito and I did some work on doing this with random forests. So the challenges are just that inference gets all the more complex. And actually, just even one thing we're working on now, and we've got some good progress, but it's not completely done, is how to extend the paper I just described to do inference with context. So I would say the easiest way to do it if you're a practitioner is actually to pre-specify, put your groups into 4 groups and just run the bandits separately by each group. But that doesn't allow you to extrapolate. If you have continuous covariates, you'd like to sort of be able to extrapolate and learn. and that's going to be much more efficient. Like if there's a single relationship with price or something like that, you're going to want to learn that relationship as one parameter, not have a 10-step function and have to learn 10 parameters separately. So the ability to extrapolate is powerful, but it's also dangerous. Just as an example, there's a paper in the contextual bandit literature that basically shows that you, as a benefit, that you don't need to experiment in some parts of the covariate space, because if you've assumed a linear functional form, you can do all your experimentation where x is low, extrapolate to where x is high, and then you already know which arm is better when x is high, therefore you don't have to experiment there. And that sort of feels kind of horrifying to someone who thinks about non-parametrics. Like what you really don't want to do is extrapolate from low x's to high x's and assume that you know what's happening in a region where you have no data. But if you go down this functional form path, it kind of leads you in that direction. And if you're not careful, that's what your algorithms will do for you. So generally, I think the ultimate promise of this should be to learn adaptive, contextual, personalized policies. And that's where the benefits will be the highest, because the higher dimension is your problem, the more benefit from adaptivity. But it's also it's a lot of moving parts. It's hard to simulate. It's hard to write pre-analysis plans, and it's hard to do inference. And that's why those are the excuses why my lab doesn't have 10 papers on this in practice already. But watch for me next year. We'll have them for sure. Right, Vitor? We've got them in the works, and we're starting to run them. But it's been harder than we thought.
So a related question to this, again, is also coming up about the dynamic nature of the adaptive element of the experiments is a question by Peter Bergman, which is how might time varying treatment effects be incorporated into this setting? If they're seasonal, could they be incorporated into the context of contextual bandit setup? And are there ways to add structure to incorporate non-seasonal time varying treatment effects? And then Burke Osler asked a question, if there's learning over time a part of, say, the implementers of the treatments, does the up or down weighting then affect things negatively? In other words, do we have to assume stability of treatment effect over time?
Great. Well, Burke is our co-author on the Cameroon project where we're doing this contraceptive stuff, and that will be a really exciting contextual bandit experiment. So I guess these time things are hard, and every dimension you add is hard. The easiest thing is like seasonality or anything else. Then that becomes a contextual bandit, and it's maybe a simpler version of context. So, if you just focus on one or two things, I think it does get easier to use contextual bandits. Now, the problem would be though, if things are arriving by season, and like right now you're all in the spring, then you're not going to be able to learn very much about the other seasons until you get there. So that's a harder problem. When things get truly dynamic, like you really have dynamic treatments, like first I want to do this, and then I want to do that, and then I want to do this other thing. First of all, the number of observations you need to do that non-parametrically just explodes. And so generally, there's very few examples of trying to actually do those things in practice without pretty strong functional form assumptions. And at some point you get into what's called reinforcement learning, which is sort of a generalization of bandits. It's like contextual bandits where there's a context, but the context is the state. So all the robots you see doing tricks and all the algorithms learning to do video games, that's basically taking a dynamic programming approach to the bandit problem. And so the context is the state you're in, whether the robot's halfway up the wall or what the state of the checkerboard is or whatever, the video game. And then you're going to be randomizing over actions according to the probability of which action is best. So all of this work is sort of on the path to reinforcement learning, which I think is an appealing direction for economists to go because we understand dynamic programming and we understand this modeling and so on. But I would just caution that the state space does get very, very large. And so unless you're in an environment where you can do lots and lots of experiments, like have a computer play checkers a billion times or have the robot just do lots and lots of tricks where it doesn't matter if they fall off the wall, then it's going to be harder to actually make that work from a power perspective under the typical way that we think about as economists of really getting kind of good, clean, non-parametric estimates of something. So you do start having to make a lot of sacrifices in terms of, assumptions or functional form assumptions or whatever else to really do those things, which I think are very important. But it's just a little bit cleaner to work at these simple cases so we understand the statistics. If you understand those cleanly, then you understand better, what's the role of the additional assumptions you layer on when you make things more dynamic.
Absolutely. I think it's a very interesting space to be working on right now, under COVID as well. So a really interesting question about replication by Moritz Paul. So in Andrews, McCloskey, Kitagawa, 2019, Inference on Winners, the authors make the nice point about regression to the mean. If there's uncertainty around treatment performance, you might end up with a winner treatment that by accident end up performing the best. So in future replications, you are almost bound to get worse results. So is it the case that with adaptive experimentation, we can reduce that problem in replication?
I would say, I mean, the advantage of taking, like, if you think in the real world, like what you're doing is actually sort of adaptive experiments, but you just didn't formalize it and you're not adjusting for it. One way to think about this is if we think about our progress of science as being a little bit adaptive, then one reason we don't replicate is because we haven't corrected for the fact that we're sort of, you know, upweighting good stuff and downweighting bad stuff in the studies we're producing. So at a meta level, I think of machine learning as a whole as helping us do better science because we're honest about our adaptivity at some level. So that's a big, 50,000 foot answer. At the more narrow level, you absolutely see within the dynamic experiments that, like, if you condition on, like, if suppose that your prior was that a bunch of things were all equal, and you run the first batch, well, of course, one of them is going to look better in the first batch. And so then, if you condition on being the highest order statistic from draws from the same distribution, your estimate of the mean should be lower than that. It's related to the winner's curse and auction theory. So, understanding that happens can be quite important. And there's a few things that you can think about. One is, again, if you take this sort of pilot view, you can use the adaptive experiment to sort of narrow things down, but then on a smaller set, go ahead and run a fully randomized experiment among a smaller set of things that's sort of replicating yourself. And that can help guard against those types of challenges where you have like a completely clean, non-adaptive data set. And if something was very important, whatever my statistical theory says, I would want to do that. But I also think that it's, it helps us reframe a little bit some of the publication bias in the sense that in some cases we may be happy to choose the thing that we expect to be the best, but also understand that, under some priors or whatever, we might expect some mean reversion. And doesn't mean the researcher was sort of not, honorable. So I think actually writing down the math of all of this and understanding what we expect to get when we're using different rules about what we're reporting and saying, oh, here we're reporting about the best arm, we need to say, well, in some cases we have enough data to really know that arm is the best and to have valid confidence intervals around that arm. In other cases, maybe, we should be worried about that we've just spuriously selected the best arm, and so we need to adjust for that. And so that the math can sort of help tell you what world you're in.
That's great. Thank you, Susan. So one last question. I know we're a little bit over time. From my experience of trying to convince companies and organizations to run field experiments, that's an effort in itself. And it's hard to do that, especially for those that don't have a large digital presence. And so this is a question related to what Galib Rustamov mentioned, which is, like, in your experience, when you've tried to convince companies to have this adaptive experimentation, what are the sort of the best ways to try and get them to be excited about this? Because there's always some like upfront costs for the experimentation. And now if we're doing then changes over time, that adds even more cost that these people in business don't really want to do. So how can we think about the practicalities of this moving forward, and any lessons that you've learned would be really helpful?
Yeah, so first of all, you never start with adaptive experiments. They're complicated for you, they're complicated for the client. So getting regular experiments up first is almost a given. Now, what you want to do is set things up though. So however you're setting it up so that you can change probabilities. And so then you can imagine going to a setting where you say, okay, we're just going to run weekly experiments. We're going to commit to you and we're going to write the scripts ahead of time that you're going to send us the data. We're going to analyze the data, and then all you have to do is just change the probabilities next week. So we need to set up a rhythm, whether it's weekly or monthly, where you send us the data, we look at the data, and we tell you the assignment probabilities again. Trying to ask them to code up the bandit in their engineering, that took even Microsoft, like 6 months, to do back in the day, 10 years ago, so it's a major engineering ask, and you don't really want to ask somebody to do it until you're sure. And you as a researcher may not be sure that it's the right thing to do, or that it's useful, or that your algorithms are working right, or anything else. So definitely, like, crawl, walk, run, like get the experimentation first. But the benefit of that pitch is, if you go to a firm and say, we're going to evaluate you for a year, and then at the end, we're going to show that your thing worked or didn't work. That's not a very appealing proposition for a firm that, say, like a young ed tech startup or something. They don't want to wait a year. It's useless in a year. And they don't want to find out that they've been doing the wrong thing for a whole year. So if instead you tell them, actually, what we're going to do is we're going to keep updating every month, and we're going to already help you improve as you go, that's a much more appealing proposition, and it's also sort of more collaborative in the sense that your tools are helping them get better. It's not about just evaluating were you good or bad. It's actually showing what's promising for improvement and updating more quickly. So that can be appealing. Also, if they're worried that some treatment you have is going to be bad, the fact that you have a plan to get rid of it or to downweight it is also very appealing for firms in some settings. So it has some advantages, but you should not understate the engineering complexity. And I generally do not start with adaptive experiments. I hold it out as the promise. We're going to get there, but first let's run a regular experiment and make sure that everything's good.
Fantastic. Thank you so much, Susan. I think we'll stop it there. I know we still got over 200 on the listening, but I think in conscious of your time, thank you so much, Susan. That was a fantastic talk. And thank you for Vito for going through all the Q&A. That was extremely helpful. Next week, we have Seema Jayachandran from Northwestern giving a talk. So hopefully see you all then. Again, Susan, thank you so much for your time. That was really enlightening. Thank you.
Thanks for being here.
Take care, everyone. Bye.